Welcome to molecular structure, the VSEPR model. Now VSEPR stands for valence shell electron pair repulsion. So molecular structure is the three-dimensional arrangement of atoms in a molecule. So how exactly they're arranged in 3 dimensions, not just the structural formula of the molecule. So the valence shell electron pair repulsion model, or VSEPR model, VSEPR theory, this says that the structure around a given atom is determined mostly by minimizing electron pair repulsions. So getting the electron pairs as far apart as we can get them and still be around the atom that they're on. So since electrons repel each other because they're all negatively charged, they want to try to get as far apart as they can. So regions of electron density, so where electrons are more likely to be, are as far apart around the atom as possible, and again, still near the nucleus. So let's look at an example like beryllium chloride. So here beryllium chloride has 2 pairs of electrons around the central atom, so around the beryllium. So the beryllium has 2 regions of electron density, one here in this bond and one here in that bond. It doesn't have any other electrons on it. It only has 4 electrons. Now, the farthest apart that we can get those electrons to be is 180 degrees. Okay, now if I have 2 balloons, imagine each balloon represents a region of electron density. So this balloon is, say, that pair of electrons, and this balloon is this pair of electrons. Now, the balloons don't want to be, if the center here is the beryllium nucleus, that knot in between my 2 balloons, the 2 balloons don't want to be squished over on one side. They're going to tend to be on opposite sides, 180 degrees apart, or they would be if they were not in a gravitational field pulling them both downwards. And so that's exactly what our electrons are trying to do. Just like the balloons are repelling each other, the electrons are repelling each other as well. So they want to be 180 degrees apart. Now, we can talk about the electronic geometry. So that's the geometry of the electron pairs around the central atom. So the electron geometry for beryllium chloride is linear. Well, because we have a linear relationship between this electron pair, the beryllium nucleus, and that electron pair. So our electron density regions are 180 degrees apart. We can also talk about the molecular geometry. So now we're talking not about the regions of electron density, but where the atoms are. So where that chlorine nucleus is, and this beryllium nucleus is, and that chlorine nucleus is. So that angle is also 180 degrees. So the molecular geometry for beryllium chloride is also linear, because again, they're 180 degrees apart. But now let's look at another example. If we have 3 regions of electron density, so now we have here boron trifluoride, we have 6 electrons around the boron, 3 pairs, so in 3 regions, 1 in each of the 3 bonds, we have a geometry that looks a bit more like this. So again, we have in the center here, we have our boron nucleus, but now we have 3 regions of electron density. If I try to squish these so that 2 of them are 180 degrees apart, that means that the other one has to have 90-degree angles to the other 2. So that's not energetically favorable. The way to get them as far apart as possible in 3 dimensions is to get them so that they're all coplanar, and they're as far apart, which means that there's 120 degrees between any 2 of them. And so this sort of geometry is a trigonal planar geometry. So here we have our 3 regions of electron density 120 degrees apart. But we also have our atoms, our fluorine atoms, bonded 120 degrees apart. So that will end up looking something like this. So we'll have our central atom, the boron, and then around it we'll have 3 of our fluorine atoms bonded. But they'll all be planar. All 4 atoms will be planar. So this is called trigonal planar. It's trigonal planar electronic geometry and trigonal planar molecular geometry. So now let's look at methane. Methane is CH4. We've got a structure that looks something like this. So we have 4 regions of electron density around the carbon. So now we will have a structure that looks something like this. We have 4 balloons, now representing the 4 regions of electron density. In the middle, we have our carbon nucleus. And around that carbon nucleus we have 4 regions of electron density that are all mutually repelling each other. Now, we could try to get these all planar so that it's a structure that looks something like this. But now we have 90-degree angles between all of these. We can get those farther apart. We can get them farther apart by giving them a little bit of energy. And now it's a 3-dimensional structure. So now we have a tetrahedral sort of structure. We're forming sort of a pyramid shape. It's not flat anymore. So now we have a molecular and electronic structure that is tetrahedral. It looks something like this. So now our 4 hydrogen atoms are bonded 109.5 degrees apart. We'll have our carbon atom in the center. We'll have our 4 hydrogen atoms bonded around. And of course our electrons will be in between, so these gray sticks represent the electron pairs of the bond. So our electronic geometry and our molecular geometry will both be tetrahedral. They'll look something like this. It's sort of drawn up here. So now let's look at 5 regions of electron density. Well, if we have 5 regions of electron density, like we do here around the phosphorus pentachloride, now we have, this is the first time we have different positions, 2 different positions within our molecule. So now we have a case that looks something like this. We've got our trigonal planar set where the 3 light-colored balloons are 120 degrees apart. And then we've got these 2 axial balloons, the white one and the dark blue one. Those guys are 180 degrees apart, and they're 90 degrees apart from the 3 axial balloons. The 3 equatorial balloons, right? So the 3 equatorial ones are the light blue ones, those are equatorial, and the axial ones are the white one and the dark blue one. And so now we've got 2 different sorts of positions. These guys, the axial ones, will be a little bit farther from the phosphorus, and the equatorial ones will be a little bit closer in. So we've got 5 pairs of electrons, and they're either 120 degrees apart, as these 2 balloons are, or they're 90 degrees apart, as these 2 balloons are. And this sort of structure is called trigonal bipyramidal, because we have 2 pyramids. So it's trigonal pyramidal in that we have a 3-sided pyramid. Right? So if we look at just the top half, we've got a pyramid here with this being one face, this being one face, and this being one face. And that's one pyramid, but then we also have another pyramid on the bottom. So this is trigonal bipyramidal. Now, in this case, our electronic geometry and our molecular geometry are the same, just like all the other ones that we've looked at so far. That's going to change soon. So that's trigonal bipyramidal. Now let's look at the last electronic geometry that we have, which is with 6 regions of electron density. Now they're all 90 degrees apart. So now we have something that looks a bit like this. So now we have 6 balloons in there. We've got 2 of the dark blue ones, 2 of the white ones, a light blue one, and a red one. And so now there's no difference between any of the balloons and any of the other balloons. I can take it in with any balloon sort of up. It looks like there's one pointing up, one pointing down, and 4 that are in a square planar geometry in the middle. But it doesn't matter which one I have up, they all are equivalent. Every position is the same. Now, this sort of geometry, I'll show you that in the molecular models. That looks like this, where we have our central atom there. In this case, we have sulfur hexafluoride, so the sulfur atom would be in the center, and each of the purple spheres here would be the fluorine atoms. So this is called octahedral, because if we draw, or if we imagine a plane on each side here of our pyramids, we have 8 sides, so we get an octahedron. And again, here our molecular geometry is the same as our electronic geometry is. So all 6 of these angles are, or all 6 of our atoms are 90-degree angles to their neighbors. So now let's look at sulfur dioxide, SO2. So sulfur dioxide has a Lewis dot structure that looks something like this. It's got resonance. We have one of the 2 oxygen atoms is doubly bonded to the other one, to the sulfur, and the sulfur has this lone pair of electrons. So this is the first time that we see a lone pair of electrons in there, which now means if we have a lone pair of electrons, the electronic geometry and the molecular geometry are going to be different. So the electronic geometry is trigonal planar because we have 3 regions of electron density, just like having 3 balloons. Each region of electron density is going to be 120 degrees apart. So we have something that looks something like this, where now we have our sulfur atom in the middle. We've got 2 oxygen atoms bonded. One of them is doubly bonded. That's these 2 bonds here. One of them is singly bonded, and then we have a lone pair of electrons that I've represented here with a stick with nothing on the other end of it. Now, the electronic geometry has 3 regions of electron density. They'll all be 120 degrees apart, like you can see here. But with the molecular geometry, we don't have 3 atoms bonded anymore. Now, if we're just looking at the atoms, the way the atoms are bonded, now we have something like this. Well, this structure isn't trigonal planar. This structure is bent. It's not linear. We can't get these into a linear geometry because this lone pair of electrons is repelling. It's still repelling those 2 other regions, even though we're ignoring it when we're looking at the molecular geometry. So the molecular geometry of sulfur dioxide is bent. Now let's look at ammonia, NH3. So ammonia has 3 hydrogens bonded. The ammonia has 1 lone pair of electrons. So we have a structure that looks something like this. Here I don't have the lone pair in there, but that lone pair, if it were there, would still be repelling these 3 other pairs of electrons in the bonding pairs. And so that will push this into an electronic geometry that is tetrahedral, because we still have that extra lone pair up there. So we have 4 regions of electron density. That gives us a tetrahedral electronic geometry. But we only have 3 atoms bonded. We have 1 lone pair, which means that our structure here is trigonal pyramidal because we have 3 things bonded, but it's a pyramid shape. It's not tetrahedral anymore because we don't have anything bonded up here. And you can see, hopefully, that the nitrogen atom is not in the same plane as the 3 hydrogen atoms are. So now let's look at water. Water has 4 pairs of electrons around the central atom, the oxygen, which means it should have a tetrahedral electronic geometry, just like the nitrogen, or just like the ammonia did. But in this case, we only have 2 hydrogen atoms bonded instead of 3, which means we get a structure that looks something like this. So again, I don't have the 2 lone pairs in. There should be 1 lone pair here and 1 lone pair there. But I don't have them displayed here. But they do cause these 2 bonding pairs to be roughly 109.5 degrees in water. It's actually more like 104.5 degrees because these guys actually get slightly closer together because those 2 lone pairs repel each other quite a bit. But water then is not a linear structure, it's a bent structure, and this bent structure for water is super important for why water is liquid at room temperature instead of a gas at room temperature, like something like carbon dioxide is, which has a linear structure to it. All right, so now let's look at hydrogen chloride. So hydrogen chloride, the Lewis dot structure is here. The chlorine atom is our central atom. That one has 4 regions of electron density, so its electronic geometry is tetrahedral still, but now we only have one other atom bonded to it, which means that now it has to be linear. That will look something like this. Again, I'm ignoring the lone pairs of electrons, the 3 lone pairs on the chlorine. We've got our hydrogen atom bonded there. It has to be linear because we only have 2 atoms bonded. Any 2 points have to be collinear. So now let's look at iodine, or triiodide, rather. So triiodide has the Lewis dot structure that looks something like this. Around that central iodine, we have 5 regions of electron density, we've got 1, 2, 3 lone pairs and 1, 2 bonding pairs. So we're going to have an electronic geometry that is trigonal bipyramidal. But in this case, instead of having 5 atoms bonded, we only have 2 atoms bonded. So what possible shapes can we get out of this? Well, we could have 2 of our iodine we could have 2 of our iodine atoms bonded in the trigonal planar plane. And that would look something like this structure. That would look something like this, where we have our axial positions, we have our lone pair here and there. We have 1 more lone pair on the equatorial position, and then on the equatorial position we have our 1 lone pair and our 2 iodines bonded. That gives us a 120-degree angle between the iodine atoms and 90-degree angles between the lone pairs. Another possibility is to take one of these iodine atoms and move it to an axial position. And for that we have a structure that looks like this. So now we have on our axis we have 1 iodine atom. We have our iodine atom in the center, of course, and we have 1 more iodine atom on the equator at our equatorial position. Now this gives us a 90-degree angle between our 2 atoms. And it gives us 90-degree angles between these 2 lone pairs and that iodine. And it gives us, with this iodine, a 90-degree angle here. It gives us a 90-degree angles between these lone pairs. And we've got 1 more possibility. The last possibility, which is over here, is this one, where we have both of our iodine atoms on the axial position and our 3 lone pairs on the equatorial positions. Now, what we want to be able to do is we want to be able to get all of our electrons as far apart as possible. But all of our regions here, they all have 5 regions, and the electrons are in the same places for each one. So initially we might say, well, all 3 of them should be possible. But here's the catch, is that lone pairs end up repelling each other more than bonded pairs do. And the reason for that is that with a lone pair, it's just a lone pair sitting there on the atom. There's nothing else around. But with a bonded pair, with this bonded pair, there's a nucleus in there on the central atom, the one that we're interested in looking at. But there's another nucleus out here, which means that those electrons are going to be nearer, they're going to be farther away from this nucleus, the central nucleus, because they're going to be a little bit closer to that other nucleus. And what it also means is that for another pair of electrons, like, say, this lone pair is going to be repelled less by the bonding pair here, because it's going to be attracted a little bit to this nucleus that's over here, that bonded pair is bonding. But with a lone pair of electrons, there's no other positive charge there to sort of mitigate the negative charge from that lone pair. Which means that lone pairs will repel lone or bonding pairs more than bonding pairs do. So what we want to try to do is get our lone pairs of electrons as far apart from each other. Lone pair interactions are the worst, so those we want to get as far apart as possible. We want to then get lone pair bonding pair far apart, and then we care least about bonding pair interactions. So in this structure, we have our lone pairs of electrons 120 degrees apart, which is as far apart as we can get them. And we have 90-degree angles between our bonding pairs and our lone pairs. So our bonding pairs are closer to our lone pairs, but all of our lone pairs, the closest lone pair interactions are 120 degrees apart. But in all the other structures, in both other structures, we've got some 90-degree angles between a lone pair and another lone pair. These other two structures are less energetically favorable. So the one that we end up with is this last one, this third one, that has our two bonded atoms 180 degrees apart. So in this case, even though our electronic geometry is trigonal bipyramidal, our molecular geometry is linear, right? That's structure C, because there are no 90-degree lone pair interactions. So now let's look at another case where we have a trigonal bipyramidal electronic geometry, but now instead of having two bonded atoms, we have three bonded atoms. So in that case, we have something like this. Again, it's the electronic geometry is trigonal bipyramidal because we have 5 regions of electron density, but now we have 3 atoms bonded. Well, we still want to get our 2 lone pairs as far apart as we can. That puts them 120 degrees apart, and now we put our atoms in 90 degrees apart, like this. 2 of them at our axial positions, and 1 of them on the equatorial position. And that now gives us a molecular geometry that is T-shaped because it looks like a T if we ignore the lone pairs. And the last possibility with a trigonal bipyramidal electronic geometry is with 4 bonded atoms, so we have a structure that looks something like this. So we again put our lone pair on the equatorial position. So if I remove that lone pair, now we have a structure that looks something like this. And now if we put it on a table, we can see that it acts like a seesaw. And so the structure there is called seesaw. So now let's look at one of the few compounds that involves a noble gas. There we have xenon tetrafluoride. So we have an octahedral electronic geometry because we have a Lewis dot structure that looks something like this. We've got 6 regions of electron density around the xenon, and we put 4 fluorine atoms bonded in all in the plane, in sort of the equatorial positions, and that gives us now, because it's all planar, that gives us a square planar geometry. It's not trigonal planar because we are forming a square here instead of a triangle. So our electronic geometry is octahedral, and our molecular geometry there is square planar. But if instead of 4 bonded atoms, we have 5 bonded atoms, but we still have an octahedral electronic geometry. But now, if I pull off that lone pair, now we have sort of our square planar geometry plus an extra one above, which means now we have still a square, but now we have a square pyramidal geometry. So that gives us square pyramidal. So that was molecular structure and the VSEPR model.